Till now we have discussed various sorting algorithms. We discussed 3 sorting algorithms with n square time complexity. After that we discussed a sorting algorithm which was based on divide and conquer technique. The time complexity of that sorting algorithm was n log n. That was merge sort. The same technique that we are going to use here, the divide and conquer, and the time complexity on an average case is also going to be n log n. The algorithm that we are going to learn in this video is a quick sort. Let's look at the sorting theory once again. Given an array that contains n elements, our task is to sort the elements in increasing order. That means we need to arrange the element such a way that they are all in increasing order or decreasing order based on the requirement. So if you look at the first array, all the elements are pretty much in random order. And if you look at the second array, elements are in increasing order, right? So this is the input array that we will get, and this is what we want to produce. So let's start quick sort. So quick sort is based on divide and conquer. We have already seen a divide and conquer algorithm, that was merge sort. So what is divide and conquer? Given an array, you are going to divide it further into smaller sections, right? So this is the portion of divide, and there is something called merge. So you merge it something like this. So now you have two different options to solve the problem, either at the time of divide or at the time of merge. The merge sort that we saw in previous video solves the problem at the time of merge, right? The quick sort solves the problem at the time of divide. So how does this algorithm works? Well, first it selects an element from the array itself. That number could be at random index or the last element or the first element. Once the element is selected, that divides the array into two different sections. One section is going to be all the numbers that are less than the selected element, and another section is going to be all the numbers that are greater than the selected element. So this is the solution that we are going to follow. Select an element. In this video we are going to select last element, okay, to solve the problem. Then we will divide that array into two different sections. First section is going to be all the elements that are less than the selected element, and the another section is going to be all the elements that are greater than the selected element. So we are going to rearrange the array in such a way that our selected element will be at correct position. So let's say this is our selected element, right? So we are going to place it into the array in such a way that all the elements to the left of it are going to be less than, and all the elements to the right of it will be greater than. Let's take an example. Example will make it much more sense. This is the input array that we have 3, 10, 2 and 5. So 5 will be our selected element. So we are going to arrange the array in such a way that 5 will be at its correct position. All the elements less than 5 will be to the left of it, and all the elements greater than 5 will be to the right of it. Look at this. 5 is placed here. 10 is now here. 3 and 2 are left of the 5. We have placed 5 to this position. All the elements which are less than 5 are to the left of it, and all the elements which are greater than 5 are present to the right of it. So this is what we want to achieve. Once we go to this particular step, we will solve it for the left array and then we will solve it for the right array. You get my point, right? So here we are solving it for the element 5. Then we are dividing the array into two different sections and solving them recursively. So merge sort solves the problem at the time of merge, while quick sort first solves the problem and then divides it. Now let's look at the approach that we are going to follow to rearrange the given array into this particular stage, right? So we are going to follow two pointer approach. In merge sort also we followed the same approach. The logic is quite different, but the technique is similar. So we are going to keep track of elements less than the selected number, right? And that will be our pointer P1. P2 is an iterator, it will move from left to right. When P2 is less than our selected element, which is a pivot element, we are going to swap P1 and P2. Why we are swapping P1 and P2? Well, P1 keeps the track of all the elements less than our selected element. So P1 will be pointing to the very first element which is greater than our selected element, right? So we need to swap P1 with P2. Why? Because P2 is less than our selected element. We want all the elements which are less than our selected element to the left of it. That's why we are swapping it. And then P1 will be incremented, or P1 will be pointing to the next element. At the end, we are going to swap P1 and our selected element, pivot element, right? Why? Because P1 will be pointing to the very first element that is greater than our selected element. So let's look at the example for the better understanding. Initially, P1 and P2, both of them will be pointing to 3. So what will happen? Well, P2 is less than pivot element. So we are going to swap it. So P2 and P1, both of them will be swapped, and 3 is going to be in this place itself. We will increment P1 as well as we will increment P2. Now P1 will be pointing to this. P2 is pointing to this. Right? Again, what will happen? We will check whether P2 is less than our selected element or not. It's not. 10 is not less than 5, of course. So we are just going to increment the P2. Now P2 is here. P1 is still pointing to 10. Why? Remember, P1 is going to keep the track of elements that are less than our selected element. So what P1 is saying, all the elements which are left to P1 will be less than 5. That's what P1 guarantees us to. Right? All the elements to the left of P1 will definitely be less than our selected element or pivot element. Okay. Now we check. P2 is less than our pivot element. Yes. So we need to swap, right? So we need to swap 2 with 10. So now here we will have 2 and here we will have 10. P1 will point 10 now, and P2 will be incremented and pointing to 5. Once P2 reaches to 5, that means the entire iteration by P2 is done. So what we will do, at the end we just swap P1 and pivot element. That means we will swap P2 and P1. P1 is pointing to the 10 now, so we are just going to swap it, and that's how we will have our final result. So this is the intermediary step and this is our final result. We will look at it further as well. But the thing is, we will use 2 pointers. P1 is going to be pointing to the very first element which is greater than our pivot element, and P2 is just a iterator that will move from left to right. Let's move forward. So now you have pivot element and it is placed in correct position. So what you do, you break the array into 2 different sections. This is the left section and this is going to be the right section. Then we will solve again. We will solve for the left section, we will solve for the right section. In the right section we only have 1 element, so no problem there. In the left section you have 2 different elements. Again 2 will be selected as a pivot element. What will happen? P1 will point to this initially and P2 will be pointing to this as well. Now the question is, P2 is less than 2? No. 3 is not less than 2. So what we will do? We will increment, and as I mentioned earlier as well, once P2 reaches the pivot element or the selected element, that means our loop has ended. We just need to swap P1 and P2. Why are we swapping exactly P1 and P2? Well, P1 will be pointing to the very first element that is greater than our selected element. So all the element to the left of it will be less than our selected element. So once we swap P1 with P2, we know that all the element to the left of it will be definitely less than our selected element. That means all the element to the right of it will be greater than our selected element. And that's what we want, right? And that's what we have said. We are going to rearrange the array such that all the elements smaller than our selected element will be left of it, and all the elements which are greater than our selected element will be on the right section of it. That's why at the end we need to swap P1 and P2, and this is what we get: 2, 3, 10. As we have already seen in merge sort, we are not actually going to divide it. See, in majority of the divide and conquer problem. Whenever we divide, we don't actually divide or split the array. We maintain two different pointers, start and end, or high or low, something like that. And by using these two iterators or pointers, you can say, we understand which section of the whole array we are dealing with. Okay, so let's look at the code. Before we deep dive into the code, I highly urge you to write your own code. We have already seen and we have already practiced merge sort. So it should be very easy for you to write quick sort, because quick sort is very easy compared to the merge sort. Okay, so let's get started. Array, we have input, we are maintaining low and high. These two variables will tell us which section of the whole array we are dealing with. So first we solve, we partition the array. Now we know the index, and based on that index we are going to divide the array into two different sections, left and right. Look at this. Here the pivot index is going to be 2, correct? So the index is going to be 2. So we are going to divide the array based on the index. So left array will start from 0 and end at 1, and the right array will start from 3 and end at 3. That's what we are doing here. We first partition. This partition will return us the index of the selected element after the rearrangement. Based on this pivot index, we are going to call quicksort again for the left portion. We are going to call the quicksort again for the right portion. Now let's try to understand the partition code. So the very first thing that I do is I select my pivot element. Here it will always be the final element, right? So I initialize P1, which is at the start, pointing to the very first element, and after that I initialize P2, which will be pointing to the very first element as well. So we start iterating on P2. We check whether P2 is less than the pivot element. Then we swap with P1 and increment the value of P1. Exactly what we saw here. I'm just writing these English sentences into the code, right? See, this is what I have written here. If P2 element is less than the pivot element, then I'm just going to swap it with P1, because P1 element I know is going to be greater than my pivot element, and I just found something smaller than the pivot element. I want this smaller element to be present to the left side, right? That's why I will swap and I will increment my P1 pointer. At the end, once the entire loop is done, I will swap P1 with my pivot element, and at the end I will return the P1 pointer. Why? Because this P1 will now hold the index for the selected element, correct? So P2 iterator is just going to iterate from left to right. P1 on the other hand will keep track of all the elements which are less than our selected element, right? So P1 will be pointing to the very first element which is greater than our pivot element. Okay, but at the start P1 will be pointing here and P2 will be pointing very beginning of the array. Okay, so now we check our P2 is less than 5 or not. If yes, it is less, then we are going to swap and P1 will be moved forward. Okay, so P1 and P2 are pointing to the very same element. So after this swap, nothing happens, but P1 will be pointing to the next element. Also P2 will be pointing to the next element. So I will just update that. Again, what we do, we check whether P2 is less than our pivot element. In this case, it's not. So we are not going to do anything. We are just going to increment the pointer P2. So now P2 will be pointing to the very next element, which is element 2. Again, what we do, we check whether this element P2 is less than our selected element or not. In this case, yes, it is less than our selected element. So what we do, we swap P1 with P2. See, P1 is pointing to the very first element which is greater than our pivot element, and P2 is pointing to something which is less than our selected element. So we need to swap and make sure that all the elements which are less than our selected element are in the left section of the array. Remove this 2 from here and remove this 10 from here. Here it will be 2 and here it will be 10. Now P1 will be pointing to the 10 and P2 will move further and point to 6. Again we will do the check whether P2 is less than our selected element or not. In this case it's not, it's 6. So we are just going to increment P2. Same thing will happen with 8 as well. Now we check again whether our P2 is less than our selected element or not. In this case, yes, it is less than our selected element. So what we do? We swap P2 with P1. Again, remember, why are we swapping P2 with P1? Well, P1 is pointing to the very first element which is greater than our selected element. And we know for the fact that P2 is less than our selected element. What we want? We want all the elements which are less than our selected element to the left side, right? So we are going to swap it. So we remove 10 from here, we remove 1 from here, 10 will go here and 1 will be here. So once the swapping is done, now P1 will move further and P2 will point to 7. Again we do the checking, right? Whether our 7 is less than our selected element or not. In this case, it's not, 7 is not less than 5. So we move further and we point to the 4. We check whether 4 is less than 5 or not. Yes, 4 is less than 5. So what we do? We swap P2 with P1. The very first element which is greater than 5 is being pointed by P1 now. Look at this. 3 is less than 5, 2 is less than 5, 1 is less than 5. So the very first element that is greater than 5 is 6 and that is being pointed by P1. So what we do? We swap this 4 with this 6. Now P2 will point to 5 and P1 will point to 8. As soon as P2 reaches to the selected element or our pivot element, we understand that the process is done. As it says, in the end we just need to swap P1 with pivot element. So P2 will be swapped with P1. Again, why are we swapping at the end again? See, P1 will be pointing to the very first element that is greater than our selected element. So this is very first element that is greater than our selected element. That means all the elements to the left of it are definitely less than our selected element. So once we swap, we know that all the elements are less than the selected element are collected to the left of it. And all the elements greater than our selected elements are collected to the right of it. And that's what we want. Correct? And that's what partition array does. It rearranges the given array in such a way that all the elements smaller than our selected element will be to the left side of it and all the elements remaining will be to the right side of it. So at the end what will happen? We will have 5 here and we will have 8. Look at this. Please make sure that you understand this because the two pointer approach is very important and the divide and conquer is also very important. Now let's look at the example. How exactly are we dividing? In merge sort, we wrote the full division operation, right? If you remember. I am not writing that full division operation here. Once you identify the partition index, you divide the array into two different sections, the left array and the right array. And now this quick sort function call will solve for this and this quick sort function call will solve for this. Remember, we are maintaining these two variables so that we can identify which exact section are we going to solve in this particular function. Let's do the time complexity analysis. See, in best case, what will happen? You select the element, that element will go to the center and divide the array into exact two portions. Same thing will keep on happening with you. You select the element and you end up dividing the array into exact two portions, right? So initially you will have one array. After that you will have two different arrays. After that you will have 4 different arrays. After that you will have 8 different arrays. Like this, at the end you will have n different arrays, right? We are dividing it until we have arrays with length 1. So the total number of steps, this we call as a step 1, this we call as a step 2, this we call as a step 3. So total number of steps are going to be log of n base 2. We have already proved this in merge sort algorithm as well. To solve one step and go to the next step, we take exactly O of n time. How? Well, we use two pointer approach, remember? And P1 and P2 are continuously incrementing. So once the number is processed, it will not be processed again. And there are how many elements? N elements. So it will take O of n times. So now we know that it will take O of n time to move from one step to another step. And we also know that there are going to be log n base 2 step. So the time complexity in the best case is going to be n into log n. So this is for the best case. Now what will happen in the worst case? So worst case is that you select the element and that number is the largest number. So you solve for the left array and there is no right array. Again the same thing happens with you. You select the number and that number again is the largest number. So you solve for the left array and there is nothing to the right of it. Again you do the same and you end up selecting the number which is the largest number. So you solve for the left array and you have nothing on the right. To move from one stage to another stage, again here also we are using two pointer approach. So it will take O of n time. But the number of steps are not just log n. They are n. Look at this. At every single stage we are removing one element, correct? So total number of steps is going to be n. So to transition from one step to another step, you take O of n time. There are total n steps. That means total time complexity is going to be n squared. So in worst case, you have n squared time complexity. In an average case, you have n into log n time complexity.